Dr. Seaborg got his AB from UCLA in 1934 and his PhD at UC Berkeley in 1937. And for the remainder of his professional career, he has remained at Berkeley with two very notable exceptions. In 1942 and 1946, he was in charge of plutonium chemistry at the University of Chicago for what was known as the Manhattan Project. 1961 to 1971, he was chairman of the Atomic Energy Commission, which is the predecessor to the U.S. Department of Energy. His current positions at Berkeley are University Professor of Chemistry, he's the Associate Director of Lawrence Berkeley Laboratories, Chairman, Lawrence Hall of Science, and Professor of Graduate School of Education. Some highlights of his career include the discovery or co-discovery of several radioactive isotopes for various applications such as medicine. Some examples are iodine-131, iron-59, cesium-137. Probably his biggest claim to fame, though, was the discovery of many of the transuranium elements, or what is known as the man-made elements after uranium, element 92. He is the discoverer or co-discoverer of elements 94 through 102, 94 of course being plutonium, as well as elements 106 and 110. And it just so happens that this past year earlier, the International Union of Pure and Applied Chemistry finally approved the ACS and the Berkeley Laboratories recommendation that element 106 is named Seaborgium in his honor. And in fact, if you look on the program, that's what the background is. He's won numerous awards, so I'm not even going to attempt to name them all here. Just a few. Of course, he won the 1951 Nobel Prize in Chemistry with E.M. Macmillan for his work with the transuranium elements. 1957, he won the Perkin Medal from the American section of the Society of Chemical Industry. In 1979, he won the Priestley Medal, which is the highest honor given by the American Chemical Society. And in 1991, he won the National Medal of Science. He's also been honored with approximately 50 honorary degrees from various universities, not only across the nation, but also across the world. And this is actually my personal favorite. Just a couple years ago in 1995, he was even honored with the naming of minor planet 4856 as asteroid Seaborg. So, if you would, please help me welcome Dr. Glenn Seaborg.
Well, no, maybe on the belt it'd be better, yeah. Right.
Here we are.
Yeah. Well, thank you very much, Mark, for your complete and accurate introduction. You made reference to the naming of element 106, Seaborgium, and that, of course, has quite a history. The Commission on Nomenclature of Inorganic Chemistry of the International Union of Pure and Applied Chemistry rejected the suggestion of the name Seaborgium proposed by the discoverers of the element because I was still alive. And furthermore, they could claim they could prove it. They could prove that I was still alive. They, however, were required to go out for comments, and they had a number of comments from, well, a large number of comments from all over the world suggesting that they'd made a mistake and that they really should allow the name Seaborgium for element 106, and so they met again last year and they reversed themselves, and now they are recommending the name Seaborgium for element 106. Today I'm going to talk about my service as the advisor to the last 10 presidents of the United States. This sort of shows what can happen to a scientist if he's not careful. And I'm going to illustrate my talk with a number of slides. The first one showing the presidents, beginning with Franklin Delano Roosevelt, whom I served during World War II on the atomic bomb project, and then going down the line as shown here. And in the course of my talk, I'm going to say a little bit about each of these. I've met all of these presidents personally, except Franklin Roosevelt, all of the first ladies, except Hillary Clinton, and all of the vice presidents serving with these presidents, there being more vice presidents than their corresponding number of presidents, because a couple of them had several vice presidents during their tenure. So I'll begin with the first. And Helen and I, my wife, saw Franklin D. Roosevelt in October of 1944, when he was running for his fourth term, when he came to Soldier Field in Chicago. And here he is appearing at that time, and we're up here in Soldier Field watching the proceedings. I met Eleanor on a number of occasions. Here, I met her at the time of the World's Fair in Brussels in 1958, and here's a picture of her on that occasion. Helen and I first saw Harry Truman when he was accepting his nomination as vice president to run with Franklin Roosevelt in 1944. We were at home in Chicago. At the time I was working on the Manhattan Project, and heard on the radio the Democratic Convention being held in Chicago, and hopped on the streetcar and went down to the convention hall and walked right in, and were able to watch Harry Truman making his acceptance speech for the vice presidential nomination. And this would be in July of 1944. And here we are over here somewhere watching the proceedings. And on that occasion, also present was his beloved wife, Bess, and daughter, Margaret. And on the after the election in November of 1944, here's a picture of Harry Truman with Franklin Roosevelt and the outgoing Vice President Henry Wallace, who I met also a little later. At the time of the early Truman presidency, I was a member of a committee, the so-called Frank Committee, that came out with a report making recommendations with respect to the use of the atomic bomb. And here's a quotation from that report. And here we ended up by making the recommendation that there be a demonstration of the new weapon before the eyes of the representatives of all the United Nations on a desert or barren island, rather than the direct use on Japan. And these are the signers of the what became known as the Franck Report on June 11, 1945. This recommendation was not taken, however, and the bomb was used, bringing the war with Japan at Nagasaki, bringing the war to an end. And perhaps that was the right thing to do, because a large number of lives, hundreds of thousands of lives, were saved on both the Japanese and the American side as a result of bringing the war to an end. Then in December of 1946, I received a call from Washington asking whether I'd be willing to serve on the first General Advisory Committee of the Atomic Energy Commission. And here's which I was glad to accept. And here's a letter from Harry Truman making this appointment. Here is a picture of Harry Truman with his running mate Alben Barkley of Kentucky for vice president soon after the election in I think on the inauguration day of January 20th, 1949, when Truman started his elective term as president. I met Truman on a number of occasions. Here's an occasion with President Johnson when we flew in Air Force One from Washington to San Francisco in June of 1965 where President Johnson was giving an address at the inaugural session of the United Nations. And here's Harry Truman, and here am I. And I met him on a number of other occasions as well. Here's a picture of Dwight Eisenhower and Mamie Eisenhower. I believe it was on their 40th wedding anniversary in 1957. In 1958, Helen and I attended a dinner in the White House and met both Dwight and Mamie Eisenhower, but I don't have a picture to show of that. I was appointed to the first General Advisory Committee, President's Scientific Advisory Committee, PSAC, and here is a picture taken when we met periodically with President Eisenhower, and here's a picture taken in December of 1960 at one of these meetings. Here's President Eisenhower, the members of the committee, and here am I in the back row. I don't know why I'm always in the back row in these pictures. And here is a cartoon of a call showing me on the telephone. Depicting my phone call from President-elect John F. Kennedy on January 9th of 1961, when I was visiting the radiation laboratory in Berkeley. I was chancellor of the Berkeley campus at that time, but I had accepted the chancellorship with the understanding that I could continue my relationship with the radiation laboratory, serve as associate director, and have graduate students working with me and so forth. And it was on one of the visits to the radiation laboratory that the phone rang, and somebody came up to me sort of wild-eyed and said that President-elect John Kennedy wants to speak to you. And he came on the line and said, Dr. Seaborg, I'd like to have you come to Washington and be the chairman of my Atomic Energy Commission. And I said, oh, gee whiz, how much time do I have to make up my mind? And he says, oh, take your time. You don't have to let me know till tomorrow morning. Well, I went home that night and told my wife, Helen, and our 6 kids about this offer. And they rebelled. They said they didn't want to go to Washington, and they demanded a vote. And so we had a vote, 7-1 against going to Washington. I mean, the 6 kids and Helen voted against going, and I voted for going. And I exercised the prerogative of the head of a Democratic household, and I vetoed the vote, and we went to Washington. Here, soon after I arrived in Washington, I arrived by the end of the month, January 1961. A couple of weeks later, John Kennedy visited the headquarters of the Atomic Energy Commission in the nearby Germantown, Maryland, and here he is entering the building there in his characteristic fashion, ready for action. And then I had a meeting with him, briefing him on the affairs of the Atomic Energy Commission in my office. And here we are with cups of tea and my favorite cookies here, Lorna Doones in front of me, and these chocolate cookies that I don't care much about in front of President Kennedy. And here I am briefing him on the elements of nuclear and atomic structure. And I found him a very apt pupil. He could follow very well what I was saying and trying to describe to him in contrast to some of the other presidents that I worked with. And here is another caricature of the I got a call from President Kennedy one day, and one of my young sons answered the phone. And he got distracted and forgot to tell me about it. And then finally he came to me and said, oh, Dad, I think somebody named Kennedy or something is on the phone and wants to talk to you. And I picked up the phone, and there he was, waiting patiently, and we had our conversation. I appeared on Meet the Press at the end of October of 1961. We had been having a moratorium on the testing of nuclear weapons since 1958, and then suddenly the Soviets began to test in the atmosphere, and the question arose whether President Kennedy was going to ask empower the United States to resume atmospheric testing. And just at that time, I was asked to appear on Meet the Press. And I knew what the first question would be. The first question would be, is the United States going to resume atmospheric testing? So I called President Kennedy and asked him how I should respond to that question. And he said, well, be very forthcoming, but don't tell him a damn thing. So I had a very interesting half hour on that Meet the Press. At that time, I appeared on the cover of Time magazine and on the cover of Newsweek magazine. This is not my favorite picture. And a little later on the cover of Business Week magazine. In April of 1962, Helen and I flew out to California, Berkeley, University of California, where Kennedy had been invited to deliver the Charter Day address. And here we are. He visited the radiation laboratory, the Lawrence Radiation Laboratory, which is now called the Lawrence Berkeley Laboratory before that, with a number of the scientists there. Norris Bradbury, the director of the Los Alamos Laboratory, came in for that occasion. John Foster, the director of the Livermore Weapons Laboratory. Ed McMillan, who was at that time the director of the Radiation Laboratory, now the Lawrence Berkeley Lab, and here am I, and President Kennedy, Ed Teller, and Bob McNamara, the Secretary of Defense, and Harold Brown, the Director of Defense Research and Engineering. On that occasion, President Kennedy gave the Charter Day address in Memorial Stadium to the biggest crowd that has ever assembled there. The whole stadium was full, and the football field was filled with people. On the way out, President Kennedy, flying out on Air Force One, President Kennedy came back to talk with me, and in order to learn something about the University of California at Berkeley. And I told him about the various people from Berkeley who were working in his administration, myself and Dean Russ, Secretary of State, Bob McNamara, Secretary of Defense, John McCone, head of the CIA, and so forth. And so that in the talk, he made his famous statement that the New Frontier owed more to the University of California than to Harvard in the people that were working with him. As I was talking with him, he was reading the text of his speech, and sort of, I didn't realize that, but memorizing it. And when he got up to give his talk there, he gave just about the whole speech verbatim without really reading or having to refer to his text. He was a very inspiring speaker, and I heard him speak many times and was always very impressed by his ability to communicate in that manner. In April of 1992, he gave a dinner at the White House for Nobel Prize winners. And here he is. And at that time, Melvin Calvin of Berkeley had just won the 1961 Nobel Prize in Chemistry. There's Jacqueline Kennedy and Mrs. Marshall is in the front row here. And here are all the various Nobel Prize winners. And where am I? Here I am in the back row. In December of 1962, we visited the Nevada test site. And here I am riding with President Kennedy. I remember on that occasion, we flew in a helicopter above the huge crater that had been made there, the Sedan crater, that was part of the Plowshare program to develop the peaceful uses of nuclear explosives. And I remember President Kennedy asking the pilot of the helicopter to set down on the edge of the crater so he could get a closer look at it. But the pilot said he'd rather not do that. He didn't think that would be very safe, and he was able to talk the president out of that. Here I am reappointed to a second term. I'd been appointed to fill out the term of John McCone the last 2.5 years of a 5-year term by President Kennedy. And then at the end of that time, he wrote me this letter, more or less saying that he was glad that I'd was willing to accept a second 5-year term. Well, he hadn't even asked me, and I was faced with the problem of what to do about it. But I just figured that if the President of the United States wants me to do this, I better do it. This was a rather clever way of his ensuring that he got my approval for a second term. I was a member of the delegation that went to the Soviet Union for the signing of the Limited Test Ban Treaty on August 5th, 1963. Here is Dean Rusk signing for the United States, and Andrei Gromyko for the Soviet Union, and Lord Hume for the United Kingdom. And here are the various members of the delegation, including Khrushchev. Where am I? Here I am, over here in the back row. On that occasion, after the signing ceremony, we went to a neighboring room for a reception, and in the course of that, Khrushchev pulled a paper with his remarks on it from his pocket and stepped up to the microphone and made some remarks. And I took out using my Minox camera, you know, it's about 2 or 3 inches high. I slipped it out of my pocket and took this picture and then put it back in my pocket, hoping I wouldn't get caught at it. And I wasn't caught, and I don't know what would happen if I had been detected doing this, but here's the picture with the Minox camera. And here's a picture of my family taken in 1964 while we were in Washington, my daughter Lynn and daughter Diane, oldest boy Pete, David, and Steve, and Eric, and Helen, and I. After President Kennedy was assassinated on November 22nd, 1963, and after he had already approved the award of the Fermi Prize, a $50,000 award of the Atomic Energy Commission, to Robert Oppenheimer, the question came up whether President Johnson would want to go ahead with the presentation, because this was very unpopular with a number of members of the Congress. And I went to President Johnson and I asked him, did he want to go ahead with the presentation which President Kennedy had approved? And I said that this would be unpopular with a number of senators and representatives, and did he want to go ahead and do it? And he just looked at me and said, Glenn, is this the right thing to do? And I said, yes. And he says, well, then the heck with the attitude of the senators and representatives, we'll do it. And that was representative of President Johnson. Here he is making the award. to Robert Oppenheimer. I had a lot of sessions with President Johnson. I remember one occasion when I was called to the White House and asked to meet with him. And I met with him the whole afternoon. And there was no particular agenda. It was just a case of the president wanting to meet with somebody that he liked and had confidence in, and we spent just sort of the whole afternoon just chewing the fat. I had actually a very good relationship with President Johnson. He pretty much approved all of my requests for money for the various projects of the Atomic Energy Commission, a number of which were actually under dispute with the Bureau of the Budget. And each year I would go down to the Pedernales Ranch in Texas, and President Johnson would have me debate with the head of the Bureau of the Budget these items in order to make a decision as to whether he would approve them despite the opposition of the Bureau of the Budget. And I went down there every year, and I had several items each year, and he ruled in my favor in every case. So I got to like President Johnson very much. And on one of those occasions, when we were driving around the ranch, as he liked to do, he had a number of, we came to a place where there were a number of quail that had gotten outside of the fence there, and he got out and chased them back in. And I told him, you know, that I thought this was quite a deal for the President of the United States to be doing, and he got quite a kick out of that. And here I am, typically getting the word from President Johnson. And he wrote me a number of letters like this, expressing appreciation for my service as the chairman of the Atomic Energy Commission. On one occasion, when I was swimming in a university club, and in those days you swam in the nude, the attendant came up sort of excited and said, President Johnson wants to talk to you. So I went to the phone, and of course I didn't have any chance to prepare myself, just answered the phone there, and he had some kind of a project that he wanted me to undertake, which wouldn't really have been feasible in my mind. And so I had to convince him right there on the spot, standing this way at the phone, that this wasn't a feasible project, and I succeeded in doing that. On another occasion, and I think it was August 1st, 1966, on the 20th anniversary of the founding of the Atomic Energy Commission, we had a reception at the White House where he met all the members of my family, and here's our daughter, Diane, and I remember his saying, "Hello, honey bun," and this pleased her very much. And here's Helen with her. And then he met my son, Eric. and my son Steve, my son Dave, my daughter Lynn. David didn't have enough sense to get out of the way here, so and my son Peter. And I also, of course, became quite well acquainted with Vice President Hubert Humphrey, and here I am at Science, just introduced him for a talk at the annual banquet of the Science Service in 1967. And I met Lady Bird on a number of occasions, and here she is at the, when she talked at the Commonwealth Club in San Francisco in the 1980s, Lady Bird Johnson and I. I first met Dick Nixon when we were both among the 10 outstanding young men of the year 1947, at the banquet in Chattanooga, Tennessee, in January of 1948. And here we are. Here's Nixon, and here am I, and here are the other outstanding young men of the year, and the Miss America of 1947. So I saw him on a number of occasions in the intervening years. On one occasion at the Bohemian Grove in I think this would have been in 1967. Here's at the summer encampment. Here is Richard Nixon, here am I, and here's Ronald Reagan. And here's one of the occasions, I think in June of 1960, when I took Lynn and Peter around to meet and talk with Vice President Richard Nixon. Here I am on another occasion with him. And he asked me in January of 1969 to remain on as chairman of the Atomic Energy Commission in his administration. Here I am meeting with him in, near the end of January of 1969. Here's Henry Kissinger and Lee Dubridge and Dick Nixon and I. And I succeeded in convincing him to give Atomic Pioneer Awards to the leaders of the Manhattan Project. Here am I and Nixon. This would be in 1970. And General Leslie Groves, the leader of the Manhattan Project, and Vannevar Bush and James Conant, the scientists who led the scientific effort in World War II. And they were given special Atomic Pioneer Awards. However, as time went on, I didn't get along as well with President Nixon, because he asked me to do things that, well, or his people, John Mitchell and others, asked me to do certain things that I thought were unethical, and I slowly fell out of favor with the Nixon administration and left in 1971 to return to Berkeley. Here is a picture of Lady Bird Johnson and Pat Nixon, taken at and Nixon and Johnson are in the background taken at the time of the dedication of the Lyndon Johnson Library in Austin, Texas, at the University of Texas in May of 1971. I knew Jerry Ford dating back from the time when he was minority leader in the House of Representatives. Here I am introducing him at a meeting of the World Future Society in April of 1974, just a few months before President Nixon resigned and he became President of the United States. I remember one occasion when I was sitting at the head table at a dinner next to Jerry Ford, and we were both rather restless, and it turned out, as we compared notes, that this was the night of the NCAA basketball final being played between the University of Michigan, his alma mater, and UCLA, my alma mater. So we stole away from the head table and went upstairs to one of the rooms and watched on TV this game. And of course, Ford was very serious about sports and was squirming there, sort of agony, because it was obvious that UCLA was rather easily winning and beating Michigan. I tried to console him, of course, but I was hoping that UCLA would win. And then after the end of the game, we went back down and took our place at the head table, and nobody had missed us while we were gone. And here we have Betty Ford at the annual convention of the American Academy of Achievement in 1985 in Denver. Oh, and I met Nelson Rockefeller, Ford's vice president, on a number of occasions. Here's one while I was chancellor at Berkeley in September of 1960, when he was campaigning for the Nixon campaign for the presidency, talking there, and here am I. And here's my son, Peter, in a rather conspicuous spot. I met Jimmy Carter on a number of occasions and was called back to the White House with others to advise him on the arms control and so forth. Here is an occasion of the annual meeting of the American Academy of Achievement in Minneapolis in 1984. Here I am with Jimmy Carter. And this is Ted Turner, the head of the CNN. And here's Rosalind Carter at that same occasion, and Jimmy Carter. In 1983, I think it was, there was a sort of a dinner in honor of Admiral Rickover, attended by 3 ex-presidents of the United States, and speaking on that occasion, Jerry Ford and Jimmy Carter and Dick Nixon. I remember on that occasion, the person who was introducing Dick Nixon was Senator Strom Thurmond. And it was a rather unusual introduction. It was more or less along the lines that Dick Nixon isn't as bad as you think he is. And poor Dick was sort of sitting there squirming through the introduction. Then I served on the National Commission on Excellence in Education, appointed by Ronald Reagan. And here we are, here am I, and here's Ronald Reagan at a meeting of that commission. They came out with the report, A Nation at Risk, that has had quite an effect on the attempt to reform and upgrade pre-college education in science and mathematics. And here I am with President Reagan with a facsimile of the report. I don't know whether I should say this or not. I'm not sure he knew what we were talking about, but anyway, we had a report. Here's Helen meeting President Reagan at one of those White House dinners. This was for a dinner in honor of Prime Minister Ingvar Carlsson of Sweden in 1987. And here am I at the same dinner, and here's Nancy Reagan. And I met President Bush the first time at a science service, science talent search function in Washington, and this was in the 1982 in the Executive Office building, and here I am with Vice President Bush at that time. Then I met Barbara Bush, along with George Bush, at a dinner at the Swedish Embassy when Ingvar Carlsson and Mrs. Carlsson, the Swedish Prime Minister, were being honored, and by the Swedish ambassador to the United States, Wachtmeister, and his wife. One day in April of 1989, I was having breakfast at a restaurant in Lafayette when a waitress came up and said I had a call from Washington, and it was someone who asked me to, could I catch the noon plane to Washington and brief President George Bush the next day on cold fusion. I don't know how much you know about cold fusion, but that was something that a couple of scientists from the University of Utah had come up with, in which they thought they could cause the fusion of light nuclei, deuterium, just by passing an electric current through a solution. You know, just very easy compared to what the physicists had been trying to do for a long time, and spending billions of dollars trying to raise the deuterium and tritium up to high enough temperatures so that they would fuse without success. And here a couple of chemists had just done it by passing an electric current through a solution of deuterium oxide, heavy oxide. And this was Stanley Pons of the University of Utah, who had found this so-called cold fusion effect, gave a talk at the national meeting of the American Chemical Society in Dallas in April of 1989. And the word got back to the White House, and well, that led to my being called to Washington to brief President Bush on cold fusion. I had to make up my mind, what was I going to do? Was I going to tell him this is a great discovery, that the chemists have proved the physicists that they'd been wasting their money all these years trying to achieve this? But I decided that on the basis of my nuclear knowledge, that that I would say it. I thought it was very doubtful, that it was very cold, that I didn't think that it was valid. So that's what I told Bush on that occasion. Of course, I told him you couldn't just go out and announce that. You have to create a high-level panel that will study it for 6 months, and then they'll come in, and announce that it's not valid. And that's what happened. They created a panel and they discussed it. They studied it for 6 months, and they came in with the conclusion that it wasn't valid. I remember on this occasion, this was just at the time that Barbara Bush had been treated with iodine-131 to alleviate her Graves' disease, disease of the thyroid. And I more or less casually mentioned that I was a discoverer of iodine-131, and that helped capture his attention. And here I am, and I think this is 1991, when Bush was the speaker at the 50th anniversary of the Science Talent Search. And here, also in 1991, in the Rose Garden, where I received the National Medal of Science from George Bush. And here's a picture with Dan Quayle. He talked to the Science Talent Search people he visited them in Washington at the National Academy of Sciences in 1990. And he went around and looked at the various exhibits, and we tried to explain them to him, and we also, his wife Marilyn understood them pretty well, and she also tried to explain them to him, but it was all to no. we didn't make any progress. And then in 1993, at the meeting of the Science Talent Search, the students, the 40 finalists, met with President Bush. And I met with him. Where am I? Well, here I am, right there. Actually, somebody called attention to President Clinton that I was in the back row there, and he came around and came back there and shook my hand and said he was honored to meet me. And then after that, I had a little session with him. He had already also heard about cold fusion at that time, and he said that he didn't quite know what it was, so he sort of had to wing it. And I tried to explain to him what the cold fusion was all about. And then I also met Al Gore on that occasion. Actually, I had known Al Gore since he was a teenager. His father, Albert Gore Sr., was a member of the Joint Committee on Atomic Energy when I was chairman of the Atomic Energy Commission. And I'd met Al Gore Jr. At that time at their home when he was just a teenager. Now I'm going to end with just a few other, showing pictures of just a few other people I've met. I met Indira Gandhi in a visit to India in 1967. Helen and I met Zhou Enlai in the visit to the People's Republic of China. We were among the first delegation to go into China in the opening up relations in 1973. There's Zhou Enlai and Helen and I. Here's a meeting of I was president of what's called the International Platform Association for a number of years. And here's an occasion in the 1984, I think it was, where I introduced Mario Como and and Jesse Jackson among the speakers. And then I met some rather attractive women, too. This is Jinx Falkenberg. I don't know, not very many of you probably remember her, but she was a tennis champion and a TV star. And I was interviewed on her program at the time of a meeting of the American Chemical Society in New York in 1957. I was supposed to be only on there a few minutes, but we hit it off pretty well together, and I think I was on there for about the whole program. Oh, and then I've met Shirley Temple on a number of occasions. Here's an occasion in the 1980s when I spoke at the Commonwealth Club in San Francisco, and she was the chairman and introduced me at that time. Actually, I'd met her the first time in 1934 when she was 6 years old, when they were filming the film with Gary Cooper, Now and Forever, at Lake Arrowhead, and some friends and I were having our vacation there, and we went by and watched the filming, and I got acquainted with her at that time. And then this is Anne Margaret. We were chosen as the co-recipients of the Great Swedish Heritage Award in 1984 in a ceremony in Seattle. And here's a picture of me with Anne Margaret, and I've been in touch with her pretty much ever since. My daughter Diane asked where in the world is my right hand here, but Actually, I got another copy of this picture and brought it home to my wife Helen, and I said, let's get this framed. And a week went by and no framing. 2 weeks went by and nothing happened. 3 weeks went by and nothing happened. And I said, Helen, how's about this picture of me with Anne Margaret? You're going to get framed. And she said, oh, didn't you know? Nobody is framing pictures anymore. So, and then finally, here I am. Thank you very much.
Although we did start a little late, I would like to open the floor up for anybody who have any questions. Just make sure you speak up and be a little clear.
Dr. Seaborg, can you tell us anything about Dr. Feynman, who was at Los Alamos, the man who wrote a book called Surely You're Joking?
Well, can I tell you anything about him?
Yeah, you apparently quite a character.
Feynman,
Yes.
Dick Feynman? Well, no, I don't know that I can tell you anything about him. He's just a sort of a genius. Very, very bright, fond of playing pranks. Wrote how have you seen his book? You know, a rather amusing book. That's all I guess I can say about him.
Dr. Seaborg, I wonder if you could elaborate at all on what it was that President Nixon wanted you to do that you found to be...
What was what?
If you could kind of elaborate on what President Nixon did to his favor.
Oh, yeah. Oh, I don't know how to elaborate on him. There was a fellow that was accused of diverting fissionable material to Israel. And it was actually wrong. He hadn't. There's no evidence, no good evidence of that at all. But John Mitchell insisted on it, and he was working for an outfit that actually handled enriched uranium, for various uses, and as a nuclear fuel and so forth. We really reached a real impasse on that. They wanted me to just summarily take away his clearance without a hearing. We always had a hearing in a case like that, but they said no, you just take it away, and I wouldn't do it. And we just reached an impasse until finally someone came up with the idea of finding another position for this fellow where he wouldn't need that kind of a clearance, and that was done. And that sort of, well, in a way solved the problem, but it really had a negative effect on his life, and he still resents it. But as I say, they wouldn't. I couldn't engage in any meaningful dialogue about it. I talked to John Mitchell, time after time, but no, just take away his clearance. No, we can't have a hearing, and that's just an example.
What do you consider your greatest contribution you've made?
What do you consider your greatest contribution made?
Mine? What was my biggest contribution? Oh, that's easy. That's finding my wife Helen and marrying her.
I was impressed by the series of films that you made in the 1950s on your work in physics. How would you advise high school students to pursue their interest in physics today?
Are you talking about the films in the 1950s? Yes. The 10 elements?
Yes.
Yeah. How would I advise students? Well, I'm often asked that question, and I give a very corny answer, really corny answer. You know what that is? Work hard, study, work hard, take good courses, in chemistry and physics and mathematics, and work hard. If you do that, then you can lead a meaningful life afterwards. And if you goof off now, you cut off those opportunities.
I think that's a very good question to end on, and I want to thank you all for your time. Thank you very much.
All right. Thank you. All right. Well, I think I'll do it.
I'd like to thank everyone for showing up. And on behalf of the Chemistry Department and the Chemistry Graduate Student Association, I'd just like to welcome you to our 20th annual Distinguished Lecture Series. It's also our second annual Derby Lecture Series in a sense. Last year, the University of Louisville has been very cooperative in helping us hold this during Derby Week. It's been real successful, and hopefully it'll be something that will continue for a lot of years to come. But there are a couple of downsides. One of the main downsides that I found is that as far as publicity goes, it's a lot harder to get publicity in this town unless you're a jockey, a TV star, or a famous house guest. But I just wanted to point out that in case you missed it, we were able to actually get some little article in the section B6 of the Metro section. I got in it at first. I was a little disappointed until I noticed that, I know nobody can see this, but in the ad right next to the article, there's a picture of Rick Pitino, so hopefully that'll be nice to see. Anyway, like I said, welcome to our 20th annual series. This year we are very honored to have Dr. Glenn Seaborg from the University of California, Berkeley. Just a little bit about our speaker before he comes up. He received his AB from UCLA in 1934. His PhD 3 years later at UC Berkeley. For the large majority of his professional career, he has spent at Berkeley with two notable exceptions, very notable. 1942 to 1946, he was in charge of plutonium chemistry at the University of Chicago for what is known as the Manhattan Project. 1961 and 1971, he was chairman of the Atomic Energy Commission, which was the predecessor to the U.S. Department of Energy. His current positions at Berkeley are the University Professor of Chemistry. He's the Associate Director of Lawrence Berkeley Laboratories. He's Chairman for the Lawrence Hall of Science and Professor at Graduate School of Education. Some of his professional highlights include the discovery or co-discovery of several isotopes and radioactive isotopes, many with various applications such as medical purposes. Just a few examples include iodine-131, iron-59, and cesium-137. Probably his biggest claim to fame, though, was the discovery or co-discovery of elements. Many of the elements past 92. He is a co-discoverer of elements 94 through 102, 94 of course being plutonium. He's also a discoverer of element 106 and 110. And it just so happens that earlier this year, the International Union for Pure and Applied Chemistry finally approved the ACS, Berkeley Laboratories, and many other people's recommendation that element 106 is named Seaborgium in the honor of our speaker today, and that is also depicted on the cover of the program that we have out front. In addition, he's also the author of the Actinide concept, which places elements 90 through 103 in what is now known as the Actinide series of the periodic table. And finally, let me just a brief summary of some of the many awards and honors this man has received. I couldn't possibly name them all, but just a few highlights include, of course, the 1951 Nobel Prize in Chemistry he shared with Ian McMillan. In 1957, he received the Perkin Medal from the American section of the Society of Chemical Industry. 1979, he received the Priestley Medal, which is the highest honor given by the American Chemical Society. And in 1991, he won the National Medal of Science. He's also been honored with approximately 50 honorary degrees from various universities, not only around the country, but also around the world. And actually, my personal favorite, I mentioned this before in the general talk, in 1995, he's also been honored with the naming of not only of an element, but also of minor planet 4856 as asteroid Seaborg. So I found that very interesting. Today, for his technical lecture, he will talk about modern alchemy. If you can, help me welcome Dr. Glenn Seaborg.
Thank you very much, Mark. As those of you who heard me talk this morning have learned, the naming of the element 106 as Seaborgium has quite a story behind it. The discoverers of element 96 3 years ago at the meeting of the American Chemical Society in San Diego announced that they were going to give it the name Seaborgium. And when the Commission on Nomenclature of Inorganic Chemistry of the International Union of Pure and Applied Chemistry met that summer, they decided not to accept that name. They rejected the name because I was still alive, and they claimed they could prove it. So this met with almost universal disdain, and they met again 2 years later, in 1996, and they changed their mind and they decided being alive is all right. And they're going to they're recommending now the name Seaborgium for element 106, and this finally needs to be approved at the meeting of the Council of IUPAC in Geneva in August, but it looks fairly straightforward. As has been announced, I'm going to talk today about modern alchemy, and by that I mean the production of these synthetic elements beyond uranium, the transuranium elements. And by the way, I'm wearing my periodic table necktie, and the reason for this is in case I forget, some of these names, I can use this as a crib, and this has pasted onto it Seaborg, the symbol SG for element 106. I'm going to start way back before the discovery of any of these transuranium elements. In 1934, when the periodic table looked like this, or really during the period before World War II. And this was the universal form of the periodic table when I first came to Berkeley as a graduate student in 1934. And the heaviest elements were placed in the periodic table up here in the body in this manner: thorium under hafnium, and protactinium under tantalum, and uranium under tungsten. And it was universally thought that the elements beyond uranium would fall into the periodic table by a continuation of that roll, so that the first transuranium element would be chemically like rhenium, eka-rhenium, and the next one would be chemically like osmium, eka-osmium, and then 95 eka-iridium, and 96 eka-platinum, and so forth. And this is the periodic table then that was used to guide the investigators who tried to synthesize and identify these elements. Of course, you would need to know the chemical properties to predict the chemical properties so that you could make a chemical separation in order to prove the identity of the new element. And actually, experiments were carried out in Rome by Fermi and co-workers in 1934. They bombarded uranium with neutrons, and they formed a number of radioactivities that decayed by the emission of electrons, which mean, of course, they would increase their atomic number, beta particles. And one of these, for example, that with a half-life of 13 minutes, seemed to have chemical properties like rhenium. It seemed to be eka-rhenium in their chemical experiments. And these experiments were carried out in Berlin by Otto Hahn and Lisa Meitner and Fritz Strassmann. And they began right after 1934 and carried on right up until 1938. And here's how they thought the situation stood in the period of about 1936-37. They produced a beta-emitting isotope, which seemed to go to an ecuranium and an eca-osmium and an eca-iridium and an eca-platinum. And these were the so-called transuranium elements. And then in December of 1938, the bottom fell out. Hahn and Strassmann, Lisa Meitner had been forced to leave Germany. She was Hitler's Germany. She was Jewish and had to leave, and she went to Sweden. Carrying on their experiments, Hahn and Strassmann found that one of the radioactivities, which they thought was due to radium, which would be, near uranium, and just knock out a few charges, you'd make radium. But they used barium for a carrier. And it was clear to them that they better be sure that it wasn't due to barium. If barium was carrying the radium, of course, barium would carry barium. And they made a very careful separation of barium and radium by a fractional crystallization method. And to their immense surprise, they found out that the radioactivity was due to barium, not radium. And this was the discovery of fission. So at this time then, we were back to square one. There were no transuranium elements. There had been 4 of them up until this time, and they all disappeared because all of those radioactivities that I showed you on the previous slides were due to fission products. Then in 1940, in the spring, here is a picture of Otto Hahn and Lisa Meitner and Fritz Strassmann, taken some years later, I think in 1956. Then in 1940, Macmillan and Abelson, using the higher intensity of neutrons that could be furnished by the cyclotron of Ernest Lawrence at Berkeley, the 60th cyclotron, bombarded uranium with neutrons and found that the previously identified isotope of uranium with a half-life of 23 minutes, uranium-239, when it decayed, actually decayed to an isotope of a transuranium element with the mass number 239 and with a half-life of 2.3 days. And this was the discovery of the first real transuranium element. And most importantly, they found that chemically, this isotope, element 93, was like uranium and not like rhenium chemically. In other words, they could deduce that the periodic table up until that time was wrong. And they tried to find the daughter of this, which they figured would decay by the emission of an alpha particle, that is a helium nucleus, would be 94-239, but they couldn't do it. They couldn't find it because it had too long, 94-239 had too long a half-life. In other words, it didn't decay very much. And they announced the discovery of the 93-239 in a publication in June of 1940. And here's a picture of Macmillan taken at that time. And here's a picture of Abelson taken at about that time. Then Macmillan started a new approach to try to find another isotope of element 93 by bombarding uranium with deuterons, and which would have the mass number 238. And he was called away for war work at MIT to work on radar, and I had been following this closely, and
when I found that he had gone, I wrote and got his permission to go ahead and continue this work. And on December 14, 1940, Kennedy, another instructor, I was an instructor in chemistry at that time, Joe Kennedy and Arthur Wall, a graduate student, made a bombardment of uranium, and we found that this other isotope of element 93, which also had a half-life of about 2 days, but most importantly, when it decayed to a detectable, an isotope with a detectable alpha particle radioactivity. And this was 94-239. And we could estimate the half-life of this on the basis of knowing this half-life and the intensity of this radiation and the intensity of the alpha emission. We could tell what this half-life was, and we estimated that it would be 50 years, which is not a bad determination, actually, because it's now known to be about 88 years. And I'm fond of saying that we had so many errors at that time that they canceled each other, and that led to a good value. Actually, now, this isotope can also be made by the neutron bombardment of Neptunium-237. I'm not going into that, but it can be made in weighable amounts, and it is now the workhorse of the nuclear space program. The heat developed by the alpha decay of 94-238 is transformed into electric power by the thermoelectric effect, and that powers the instruments that sends the signal back to Earth in the space program, which, by the way, you never hear about when you read about these space flybys. Here's a picture of me taken at that time in 1941. And I like to show this picture because it shows how little I've changed in the last 56 years. And here's a picture of Joe Kennedy taken. Joe Kennedy and I went down to Los Angeles at Christmas time to visit my parents, a little suburb of Los Angeles called Southgate, leaving our graduate student Arthur Wall at Berkeley to continue the work. And here's a picture of Joe taken in our backyard in Southgate with my mother's box camera, Kodak camera. And here's a picture of Wall taken at his office in Washington University right after the war. Well, then we had the privilege of suggesting a name for the element we've discovered. And because uranium had been named after the planet Uranus, and Macmillan had suggested, therefore, that Neptunium should be named after the next planet, Neptune, we decided to name our element 94 after the planet Pluto. We didn't come to that conclusion immediately. We thought that we had reached the real top. You know, nobody would ever get higher than this. So we thought we should call it extremium or ultimium. And think how foolish we would have been if we had done that. Actually, using this base Plut, we probably should have called it Plutonium. But we liked Plutonium better. Plutonium, it just seemed better. And we should have given it the symbol PL, but we like PU better. So we gave it this, we suggested the symbol PU, and we thought that we would be criticized for this. Here is the publication that was published. Actually, this was sent as a secret report. This information was sent, all of this was sent to Washington in a form of secret reports. We held it voluntarily secret. It was not government-supported work. It was just our own faculty and graduate student research. But we held it voluntarily secret for a reason you'll see in a moment. And it was reported to Washington in a report submitted on March 21st, 1942, and then declassified and published in the Journal of the American Chemical Society in 1948. And here's the actual wording in which we suggest the word plutonium and the symbol Pu. And I had the pleasure of meeting for the first time in 1991 in Albuquerque, New Mexico, in a visit I made there. Clyde Tombaugh, the discoverer of the planet Pluto. He was still alive. He discovered the planet in 1930, but he was only 24 years old at that time. And here we are at a press conference, the discoverer of Pluto and plutonium holding forth. Now, I dictated those reports on this early work on plutonium to Ernest Lawrence's secretary. Ernest Lawrence was the great physicist at the University of California, the inventor of the cyclotron, for which he received the Nobel Prize in Physics in 1939. And I'm fond of saying that this girl named Helen Griggs was so efficient in typing these reports, that I decided to try to date her. I think she prefers another characterization, and I have to agree that she had other qualities as well that led to my wanting to date her. And here we are in San Francisco on Christmas Day, 1941, where we went for dinner. And an itinerant photographer, one of these people that took a picture and then handed you a card, and then if you sent in a quarter or whatever it was, you'd get a print of the picture, which I did, and so we have this picture taken on December 25th, 1941 on the sidewalks of Market Street in San Francisco. And the room in which the chemical identification of plutonium was made, February 23rd, 24th, the night of February 23rd, 24th, 1941, was on the 25th anniversary declared a National Historic Landmark. And here we are on that occasion, and there's a plaque outside that room, room 307 in Gilman Hall at Berkeley. It's the only one of the original chemistry buildings standing, for which I'm just thankful. We're just very lucky that that's still there. And if you ever go to Berkeley, you can go there and you can see the very room where the plutonium was discovered, which has this plaque on the outside. Here am I, and here's Art Wall and Ed McMillan and officials from the Department of Interior that made the designation of this room as a historic national landmark. After the discovery of plutonium-238 through the isotope 238, we, joined by Emilio Segre, made a bombardment of a large amount of uranium, pounds of uranium, where we had been bombarding just grams for days, where we had just been bombarding for maybe an hour or two, and isolated the Neptunium-239 we could estimate that we had to produce an actual weighable amount, 0.5 of a microgram. We didn't weigh it, but I mean it's a ponderable amount, and this is the first time that much had been produced by any transportation reaction, which when it decayed, we could detect the activity. We knew we had 0.5 of a microgram, and we could detect the activity and estimate its half-life from the intensity of the activity, knowing how much of this we had in its half-life, and we estimated that its half-life would be 30,000 years. And that's not a bad determination either, because today the half-life of plutonium-239 is known to be 24,000 years. It's another case where we had so many errors that they canceled each other, and we came out with a pretty good value. And this determination of the fissionability of plutonium-239 was made on March 28, 1948, using the neutrons from the neighboring cyclotron, the 37-inch cyclotron, and we showed that the fission probability, the fission cross-section for plutonium-239 was as large as that of the fissionable isotope of uranium, U-235. And of course, we reported this to Washington and kept it secret, obviously, because this meant that it had the potential, the plutonium-239, to be the explosive ingredient of the atomic bomb. And this led to the Manhattan Project, the plutonium part of the Manhattan Project. And I moved, here we are on the 25th anniversary of that determination, which would be March 28, 1966, where Gray and I are presenting this original plutonium upon which the fission was demonstrated on March 28, 1941 to the Smithsonian. And it's now on display there in the Science and American Life exhibit of the history building of the Smithsonian Institution, if you want to see it. Actually, the Smithsonian got in touch with me and wanted, at the time of the 25th anniversary, and wanted to know whether I could present them with this original sample upon which the fissionability of plutonium-239 was demonstrated. And I was in Washington then, serving as chairman of the Atomic Energy Commission, and I decided, I thought I knew where this sample was. I thought I had put it in a cigar box. I had served as Gilbert Newton Lewis's personal research assistant the first 2 years after I received my PhD. And he was an incessant smoker of Alhambra Casino cigars, 5-cent cigars. And I inherited these cigar boxes. And I recall that I put this sample in the cigar box and put it in a cubbyhole in room 307. So I phoned Berkeley and told them to look there, and they did. They found it, and they shipped it to Washington, and we presented it to the Smithsonian, and that's where it is now. Here's the way the Berkeley campus looked at that time. This probably doesn't mean very much to you if you're not familiar with Berkeley, but there's Bancroft Avenue and Telegraph Avenue. They had stores along here and so forth. This is all campus now. And our buildings where we did this work, the chemistry buildings and the radiation laboratory buildings where the cyclotrons were, are up here. Here is the famous campanile of the Berkeley campus. And here is the Crocker laboratory where the 60th cyclotron was situated. It was situated right here in this high part of the building. This is the old freshman chemistry laboratory. And here is the old radiation laboratory where the 37-inch cyclotron was situated. Actually, my first laboratory, when I came to Berkeley in 1934 as a first-year graduate student, was this room right here. And this building, of course, has, in the meantime, been torn down to make room for modern buildings. Oh, this is just to show you some pictures of plutonium in its 5 oxidation states, 3, 4, 5, 6, and 7. And here are the different forms of plutonium in the 4 oxidation state, different solutions. It's a very versatile element. It can exist in equilibrium with detectable amounts of 4 oxidation states at one time, and its metal has also almost unique characteristics with its many phases. But then I was called to Chicago. With Pearl Harbor coming along, the decision was made to assemble a large effort in the atomic bomb project, and the plutonium part was centered at Chicago, at the so-called metallurgical laboratory of the University of Chicago. And I went to Chicago and took some of my key people with me, arriving in Chicago on April 19th, 1942, my 30th birthday. Now, I wasn't about to leave Berkeley without making a deal with Helen, and, well, some people would say I proposed to her, and she accepted me, and I came back to Berkeley 6 weeks later, and she joined me there, and we went down to Los Angeles, where she met my parents. And here's a picture taken in that same backyard of my parents' Southgate home with my mother's box Kodak camera on June 5th, 1942, the day before Helen and I were married. We took the train that night to Nevada, and we looked on the map, and a good place to get off, where we would come in at about 10 o'clock in the morning, was a town called Caliente. And we thought, all right, we'll get off there and we'll get married there. So we got off at Caliente and talked to the station master and said, we want to get married. Where can we get a marriage license? And he said, not here. And I said, well, where then? He said, well, in the county seat, where else? You know, and I said, well, where's that? He said, that's in Pioche, Pioche. And I said, well, where's that? And they said, well, it's about 25 miles north of here. I said, well, how do we get there? And he said, can't get there from here. And what he meant by that was that it was Saturday, and the courthouse was closed in Pioche. Well, actually, the buses that ran up there, the public transportation didn't run on Saturday. That's what he meant by can't get there. And so we were on the spot. A young chemistry graduate from Berkeley saw me and recognized me, and he knew about our problem, and he said he thought he could help, and he arranged for us to ride up on the mail truck. And so Helen and I got in the front seat of the mail truck and rode all the way the 25 miles up to Pioche, helping them, the mailman deliver the mail on the way to Pioche. then we got married and came on back down to Caliente and then went on to Chicago. At Chicago, we had the problem of developing the chemical processes for the separation of plutonium from the uranium and the high level of fission products that would be produced in the chain reactor, or the pile as it was called. Enrico Fermi had the responsibility for developing the chain reactor, the pile, to produce the plutonium, and I had the responsibility for working out the chemical processes which would have to work by a remote control due to the huge amounts of radioactivity, the chemical processes that would be used for the separation of plutonium from the uranium and the fission products at first at the pilot plant at Oak Ridge, Tennessee, and then at the huge production plants in Hanford, Washington. But we had to test this at the actual concentrations that would exist, this process. We had to test it at the actual concentrations that would exist at Hanford. We'd worked it out just on the tracer scale, carrying invisible amounts of plutonium. And we couldn't be sure that such a process would work. We had to be sure it worked at the concentrations that would exist at Hanford. And that posed a problem, and I had the idea that if we could bombard huge amounts of uranium, hundreds of pounds, for a month at a time, we could produce micrograms of plutonium. And then if we could dissolve those in microliters, micrograms per microliter would be grams per liter, which would be the approximate concentration to be found in the Hanford chemical separation plant. We could test the process if we could learn how to work with microliters of solution. And this is the field of ultra microchemistry. And I was able to find some people, Burris Cunningham and Louis Werner, and they worked on this ultra microchemical scale and tested the process and found that it would work, the process that we worked out. And here we are on the first day that they isolated a visible amount of plutonium. This would be August 20th, 1942. And here they are in the little room, 420 Jones Laboratory at the University of Chicago, which on the 25th anniversary of this day was declared a historic national landmark. And here I am looking at it, at that first microgram of plutonium hydroxide on August 20th, 1942. It's room 405 Jones, I think I said 420, 405 Jones Laboratory. And then Cunningham and Werner weighed the first plutonium. They isolated 2.77 micrograms of the oxide, and on August 10th, 1942, used this microbalance made of quartz fiber. Here's the arm, and here's the holder for the weighing pan here, and the amount of depression there could be measured, calibrated, and measured with a telescope, and that would relate to the weight, and they could weigh the plutonium to an accuracy of 1%, the 2.77 micrograms. And here's a picture of the first plutonium weighed, held here by the forceps here, and the oxide is here. And this is on display at the Lawrence Hall of Science, the Lawrence Memorial Room in Berkeley. Well, now, we thought we had the thing under control, that we would try to find the next two elements, the elements with the numbers, atomic numbers 95 and 96, which we thought would be chemically like plutonium, neptunium, and uranium, because these seem to be chemically alike. We thought there'd be another rare earth series in which the 14 5f electrons would be filled in, just like these 14 4f electrons are filled in here. This is called the lanthanide series, and this would be a uranide series. And so we effected certain transmutation reactions that would produce elements 95 and 96 and try to make a chemical separation on this basis and failed. We're wrong again. Just slow learners. In retrospect, we threw the samples containing the 95 and 96 down the drain because we had the wrong chemical theory as to how they would be fit into the periodic table from which we could make predictions about their chemical properties. We had to know their chemical properties because we had to separate an extremely small amount of the 95 and 96 from immense amounts of other radioactivities and so forth. Then I got the idea one day in 1944 that maybe the periodic table was wrong, that we should move these elements here down here and form another series called the Actinide series. And then when you count on over, if you didn't make a mistake, then element 95 would be chemically like europium, and 96 chemically like gadolinium, a whole new ballgame. And when we did that, we were able to identify the next two elements with the atomic numbers 95 and 96, which we gave the names americium and curium. And then obviously you could predict the chemical properties of the rest of the elements, 97, 98, and so forth, up to 103. And then we'd go up to here and put 104 and 105 and 106 in those positions. Now there's an interesting, and here's a picture of Al Giorso, my co-worker on this work on elements 95 and 96, who taken in Chicago shortly after that time, but who has been associated with me in this research on the transuranium elements ever since. And then there were two young bachelors, chemists, Ralph James and Tom Morgan, who worked with me on this discovery of elements 95 and 96. Now, the announcement of the discovery of these elements was made under rather unusual circumstances. I was asked to be a guest on the Quiz Kids program. This is a program in which questions were sent in by the listening audience, and the quiz master, Joe Kelly, asked a number of kids aged from 5 to 15 these questions, and the kid who had the correct answer received a prize, a war bond at that time. I was asked on Armistice Day of November 11th, 1945, to appear on the Quiz Kids program, and they turned the program around so that the kids asked me questions on the last half of the program. And one of the kids asked me, I had received clearance to announce the discovery of elements 95 and 96 the following Friday. That would be November 16, 1945, at an American Chemical Society symposium at Northwestern University. So I'd gotten that clearance. So in this Quiz Kids program, one of the kids asked me if there had been any new elements discovered at Chicago there in the metallurgical laboratory during the war, and I said yes. I blurted out yes. There had been the two elements with the atomic numbers 95 and 96, and that was the announcement to the world of the discovery of these elements. Now, the interesting thing here is that that program, as it went out over the air that night, November 11, 1945, was recorded on one of these 78 RPM discs, and a copy of that was sent to me, and I've had that transferred to a cassette tape so that you can hear exactly how that program went out over the air on November 11, 1945. Let her roll. First of all, there's the introduction. And the kids are introduced.
Thank you, Bob Murphy, and good evening, everyone. Well, children, we have the great honor to present as our guest observer on this Armistice Day program a most distinguished scientist, Dr. Glenn T. Seaborg. Dr. Seaborg was a co-discoverer of the new element plutonium at the University of California, and he was closely concerned with the development of the atomic bomb at the University of Chicago. Because the whole world is rightfully curious about the atomic bomb and its grave implications for world peace or world annihilation, it seems a very appropriate subject for our Armistice Day discussion. We're going to reverse roles in our final question session and let you children quiz Dr. Seaborg on the atomic bomb. I hope you'll have some good solid questions ready for them. Now, let's get roll call started. Harvey?
I'm Harvey Bennett Fishman. I'm 15 years old, and I'm a sophomore at the South Shore High School. Well, Doctor, do you really think they'll be able to harness the energy of the atom and use it for driving ships or planes in the post-war world?
Well, Harvey, yes. I think they will. Not right away, but sometime in the future, say 10 or 15 years.
Richard, how about your question?
Well, Doctor, how long do you think it'll be before some of the more stable elements will be split, that is, on a practical scale? Oh, on a practical scale. They've been split on a small scale. On a practical scale, I don't know. A new principle would have to be discovered, or a new type of reaction. However, it's probably, I wouldn't say that it'd be impossible, maybe in 50 years or so. Well, another thing,
Here it is.
have there been any other new elements discovered, like plutonium and neptunium? Oh yes, Dick. Recently there have been two new elements discovered, elements with atomic number 95 and 96, out at the Metallurgical Laboratory here in Chicago. So now you'll have to tell your teachers that to change the 92 elements in your school books to 96 elements.
We didn't have Dr. Seaborg at the microphone for the entire half hour. We certainly thank you, Dr. Seaborg, for taking time from your many pressing commitments to be with us tonight. This is Joe Kelly dismissing the Quiz Kids class until the same time next Sunday when we'll broadcast from Youngstown. Good night, kids.
Good night, Mr.
Listen to the Quiz Kids every Sunday, and listen to your old friend Lum and Abner every Monday through Thursday. Folks, check your family supply of Alka-Seltzer. And remember, when your tablets get down to 4, that's the time to buy some more. This is the American Broadcasting Company.
Then we returned to the University of California at Berkeley. Well, I did, and Al Giorso and some of the others. And we began to seek methods of producing the elements still heavier. And in order to do this, we needed heavier isotopes to bombard. So we bombarded plutonium with neutrons in high flux reactors. And then that way you added neutrons, increased the atomic mass until it got an excess of neutrons, and then that nucleus emitted electrons, and you worked your way up to scale this way till you went all the way up to actually fermium 257. And we made the bombardment. I'll skip over a few elements, but in 1955 we made this bombardment. We had a total of about 1 billion atoms of Einsteinium, and we could calculate, therefore, that we produce one atom of the new element 101 with the mass number 256 per experiment. This is the way the experiment was set up. The helium ion struck the target of Einsteinium, and then the element 101 atoms were recoiled out so the target could be used over and over again. And then the 101 was caught on this catch-a-foil, and then that was dissolved and the chemical separation made. by what is called the ion exchange adsorption elution method. Like this. This is a piece actually that appeared in the Soviet journal Priroda, the alpha particle striking the target, Einsteinium, the 101 being projected out, and then the catcher with the element 101 atoms dissolved, and then put through an ion exchange column where they're adsorbed and then dissolved or eluted. They come out in the inverse order of the atomic numbers, and then they were detected with the detection apparatus. And it was, we discovered one atom per experiment, actually, and announced to the world the discovery of the new element for which we suggested the name mendelevium. So, up until this time then, up until 1955 and 56, we'd use neutrons and protons and deuterons and helium ions for all of the experiments, but we couldn't go further without bombarding with heavier ions if we're going to get a still higher atomic number, carbon, nitrogen, and oxygen. So we had to build, beginning in 1956, a heavy ion linear accelerator for this purpose. And here is the tank for the heavy ion linear accelerator coming up the hill in 1956 at Berkeley. And they have this hairpin turn there in going up. The campus is down below. And there was a fear that this tank, weighing 50 or 100 tons, would break loose and roll down on the campus in the city of Berkeley. And in order to be sure that wouldn't happen, it was tied with this rope here to that tree up at that We just took every precaution. Then we went on, skipping a little bit, on to element 106, which was actually discovered in 1974 by this method. An isotope was found that could be identified through the identification of its daughter and granddaughter previously known. So that all you had to do was add an alpha particle to this, helium-4, charge 2, add 2, and add 4, and that would mean we formed element 106, 267. And here's the team that did that work, a picture taken in 1974. There's Al Garso, Matty Normio, and I'm here, Ron Lougheed and Ken Hewlett and the Alonzos, Carol Alonzo. And here are and Jose Alonzo. These are the discoverers. And you've seen this picture. The decision was made 3 years ago. We couldn't suggest a name because there was a competing claim from the Soviet Union. And there was a group, a transfermium working group appointed by IUPAC and IUPAC that went over the evidence and data and decided that our team was the discoverer of element 106, and the name Seaborgium was suggested. Now I'm just going to go through quickly here. The next elements beyond this were discovered actually in the GSI laboratory in Germany in 1981. They bombarded bismuth, which has a closed shell of 126 neutrons, which makes it very stable and low mass, so that this will be at a low excitation energy and reach the ground state by the emission of only one neutron. And they were able to identify the 107 by this method of genetic relationship, identifying previously known daughters and granddaughters. And then here's the 1982, they've similarly found an isotope of element 109, and then an isotope in 1984, an isotope of element 108, identified with these, and then some more isotopes, and then identified by these genetic relationships, identifying that the isotopes decay to previously known daughters and granddaughters. And then in 1991, a team headed by Giorso at Berkeley bombarded cobalt. The reason these work is that these are tightly bound because they have closed shells of 126 neutrons, and here 126 neutrons and 82 protons. And Giorso et al. Formed this isotope and found one decay chain. And then in 1994, the GSI group, Sigurd Hoffman et al. Found these isotopes. And then 1995, a group at the Dubna laboratory found this isotope, identifying also always by the chain, the genetic relationship to known daughters and granddaughters. And then here in 1994, the GSI group in Germany found this isotope of element 111, and by Hoffman and co-workers, and 112. By these reactions, and again identified through the decay to the previously known daughters and granddaughters. So here's where we stand today then. We have all these isotopes, actually 20 transuranium elements. The last three haven't been named yet, and the others have had these up through here have had their names under dispute, but the latest recommendation of the Commission on Nomenclature of Inorganic Chemistry of the IUPAC is that these names be accepted, that this Berkeley name be accepted. I'll skip this, that Seaborgium be accepted, and then these three names be suggested by the GSI laboratory be accepted. But for element 105, the Commission on Nomenclature recommended the name dubnium under to recognize the group at Dubna in the Soviet Union. But we believe that they were not a discoverer. Their work came in second, and that the name suggested by the Berkeley group should be used, honium. Even if the name dubnium is accepted at the meeting of the Council of the IUPAC at Geneva in August, a large part of the scientific world is going to continue to use the word honium for element 105 because it's been used for 25 years in the literature, and it'd be chaotic to change to something else. Now, this is where we stand today then. There are the natural elements and the known transuranium elements, 20 of them. But it's also been predicted that there should be closed shells magic numbers of nuclei that increase the stability of elements in this region, especially around element 114. Here is a prediction of some of the chemical properties of these elements, should they be found. I won't dwell on this. But the idea is that there should be closed shells of neutrons. There are known to be closed shells, points of stability of neutrons with these numbers and protons with these numbers, and it's predicted that at 114 protons, here, 114 protons, there should be a closed shell, and 126 neutrons. These are the closed shells of electrons leading to the noble gases, and it's sort of by analogy with these that we can point to these closed shells, points of increased stability, closed shells of protons and neutrons. So we look for a closed shell at element at 114 neutrons. And many attempts have been made to produce that, but we haven't succeeded yet. There's the thought that this might stretch out a little bit and have what they call an island of stability centered at these points, these closed shells, or these magic numbers. And that would be sort of like this, where if you plot all of the known nuclides, all of the known isotopes, atomic number against neutron number, they fall on a peninsula like this, and then there would be an island of stability out here at atomic number 114. And the way this would be produced would you be bombarded a nucleus with a heavy ion, get an excited state, and then you would hope that this could reach the ground state by boiling off neutrons. But by far the main reaction is fission products, and it's something like 99.999999 plus % going into this reaction, and there's very little left over to form the new elements. In fact, the elements with the atomic numbers at the very top, like 110, 111, and 112, the reactions to produce them produce only about 1 atom per week, or 1 atom per 2 weeks, and the half-lives get shorter and shorter, and until they're down in the region of microseconds. But there is some hope that maybe by bombarding curium-248 with calcium-48, which has a closed shell of 20 protons and a closed shell of 28 neutrons, you might be able to get a reaction like this to form an isotope of element 116. And here are some other possible reactions to produce these elements. And another possibility is the trouble is we can't get enough neutrons into the nucleus. And in order to do that, it might be possible to produce neutron excessive isotopes, isotopes that have more neutrons than exist in stable isotopes, radioactive isotopes. And then by having a large enough beam, produce enough of these radioactive isotopes, like calcium-52. So when you bombard curium-248, you can get up to here where you have 184 neutrons and 116 protons, which might enable you to get to a closed shell. That's, if you could use such radioactive beams, you have all of these possibilities. In addition to the stable isotopes, you have a whole range, literally a couple of thousand of isotopes that you can bombard with to try to produce still heavier elements. And I won't dwell on this. This is just a kind of a diagram of a kind of an apparatus that might be used to produce such radioactive beams for such experiments. Now, I don't know if there's any use to put this on, but a number of periodic tables have this IUPAC scheme that they suggest for naming elements before they're discovered. Like 111, they'd name yum. It would be the symbol would be or whatever. And we think this is crazy. All the investigators in the field think this is crazy. And if you have a use for wanting to write the dioxide of element 111, just do this. Just put 111 in parentheses and O2, and don't try to put O2. And so here we are then at the end. Here's the periodic table of today. Goes all the way up to element 112, known isotopes. And we can predict with complete surety that we're going up to the next noble gas at element 118. The only trouble is that probably due to the fact that the half-lives are getting so short and the yields are so small, it won't be possible to go maybe all this way, maybe up to about 100, well, maybe another 6 elements or so as we get better beams of radioactive ions and better beams of stable ions and better detection techniques and so forth in the coming years. And then here's finally a periodic table, the sort of end-all periodic tables. Here is the after 118, I put the next element up here, element 119, as the next alkali metal. See, it'll fall in this column. And then 120, the next alkaline earth. And then when you get to 121, you get another inner electron series. Like here you have the 14 4f electrons. Here you have the 14 5f electrons. Here you should have the 14 6f electrons and the 18 5g electrons. See, when you get to this shell, you have room for a quantum number G, where you have S, P, D, F, G, which would have 18 places, and they'd be filled in the commingling place manner, so that you'd have 14 plus 18 equal 32, and get you up to element 153, and then up here at 154, you'd get back up in the body of the periodic table, as shown here under Rutherfordium, and then on across to element 168, which would be the next noble gas. Actually a noble liquid, because its boiling point would be above room temperature. Now this is something we are confident would be the form of the periodic table, if it, but whether it can be confirmed or not is very doubtful. In fact, probably not possible, because the isotopes are too short-lived and the yields are too small. I think you'll probably only get up, as I say, another half dozen isotopes or so. And with the modern high-speed computers, it's been possible to verify this and to calculate that these electrons should fill in to these shells in the manner shown by this periodic table. That's it. Thank you.
Right now, Dr. Seaborg would be happy to answer a couple of questions anybody in the audience may have. Just make sure you speak up and try to be pretty clear. I'm sorry, go ahead.
Could you comment on the nature of the separation process to isolate the little amount of plutonium from the fission product?
Well, the isolation process that we worked out for plutonium was to carry it, you know, the co-precipitated with a precipitate of bismuth phosphate, precipitated from acid solution. Now, we chose that because bismuth phosphate has a crystalline precipitate, which could be centrifuged out, you know, by remote control and give us an operable process. The other possibility was to carry it with lanthanum fluoride, which is a sort of a gelatinous precipitate and very hard to handle. And we had to make a choice between those two processes, and I finally had to make the recommendation, which was probably the hardest decision I ever made in my life, and the one for which I received the most criticism that I've ever received, because bismuth has the valence, the oxidation number of 3, see, bismuth phosphate, and plutonium had the oxidation number of 4. So plutonium-4 phosphate shouldn't carry with bismuth phosphate. And so the people said this was the Seaborg's boondoggle. You know, he was recommending a process that couldn't possibly work. And actually, that was one of the reasons I had those ultramicrochemists work. And I showed that it would operate at the actual concentrations that would exist in the Hanford plant by carrying out these experiments on the ultra microchemical scale. And it worked right from the beginning. At Oak Ridge gave good yields, and within a few weeks at Hanford gave yields more than 90%. But boy, that was a tough decision. And, it was really going against the experts. You know, they said that this was just crazy. And if it hadn't worked, we wouldn't have gotten the atomic bomb on time. It was a tough decision, I can tell you.
When you first isolated plutonium, Dr. Seaborg, did you have any idea it would be as toxic as well as radioactive?
Did you, when you first tested plutonium, did you know it was going to be as toxic or radioactive?
Yeah, we knew that plutonium was toxic, radioactive. It was an alpha particle emitter. We knew about the work of the radium dial painters, you know, and the people who would poison themselves by ingesting this alpha emitter. But, well, I like to say facetiously, we had such a small amount we couldn't afford to ingest it, but that wouldn't, actually, it turns out that this is a gross exaggeration, that plutonium is the worst poison known to mankind. There are many poisons that are more toxic than plutonium. You know, toxins, viruses, all kinds of biological substances that kill you right away. And in the case of plutonium, if it's ingested, you get a slow deterioration of tissue. There were a number of people that ingested plutonium at Los Alamos and Hanford more than 50 years ago. And they're still alive, but they're all going to die.
What is the heaviest element for which there is traditional wet chemical evidence for the chemical properties?
Seaborgium. Actually, they have discovered a couple of isotopes of Seaborgium that have half-lives as long as about 10 or 15 seconds. This makes it possible to do chemical studies. And in the last couple of, the first publications on this are just appearing. And they have established that it is indeed chemically like tungsten. See, it should be ecotungsten, and it is indeed chemically like tungsten. And so I'm now looking forward to the time when I can read in the literature about Seaborgus chloride, Seaborgate nitrate, sodium Seaborgate, and so forth. I think that's going to be lots of fun to read that.
When you headed the Atomic Energy Commission, atomic power was on the rise. After you left, it has just about died. At least new plants are not being built. I'd love to hear your comments about what's happened in nuclear power.
Well, the anti-nuclear people just went out, except in France. France is developing 75% of its electricity from nuclear energy. Economically, they can export electric energy, and are not contributing to the greenhouse effect and acid rain and air pollution that we have from the burning of fossil fuels. Actually, the most benign method of generating electricity is from nuclear power. Nobody's ever been hurt from that in the United States. And you would get around the greenhouse effect, the acid rain, the air pollution, the 100,000 of coal miners that have black lung disease and so forth. All of that is avoided by using nuclear power.
That's all the time we have, and I'd just like to thank everyone for coming, both the one before and also today. Thank you. Hope to see all of y'all next year. Thanks.
So